My name is BAAMRANI. I am PhD student from Faculty of Science, Ibn Zohra University. It is a great opportunity for me to present my research in this conference, and the presentation title today is Numerical Study of Heat and Mass Transfer in a Desalination System. To abort this presentation, we have this outline. First, we have an introduction, secondly, the physical model, then results and discussion, and finally, conclusion. In the last 10 years, the natural convection phenomena in a closed cavity is the subject problem interest for many researchers. This is due to its applications in various industrial sectors, such as solar desalination, distillation, packaging of semiconductors, and electronic chips. In fact, the characteristics of heat transfer and the flow field for the natural convection problem in a cavity channel are investigated. The objectives of these works are to numerically study the evaporation of a thin liquid film in a closed cavity and to study the effect of various parameters on the heat and mass transfer. The studied configuration is a vertical channel formed by two parallel flat plates for height h and distance from B. As you can see in this figure, this liquid film enters the channel with a mass flow d and a temperature T0. A uniform heat flux density Q is applied to the wet wall. The following simplifying assumptions are taken into account. The flows and transfers in the two phases are laminar and incompressible. The liquid and gas flows are two-dimensional and transient. The channels walls are supposed very thin. Taking into account the simplifying hypothesis, the governing equations for continuity, momentum, and energy equations in a two-dimensional can be written as listed below. For numerical modeling, all domain is meshed using structured mesh. The finite volume method is used to solve the above equation system, and the results of this study are obtained using ANSYS software. The case step of the finite volume method is the integration of the dimensional governing equations over a two-dimensional control volume. As a result, the effect of water inlet flow rate was examined. To analyze its influence, we present the local variation of temperature for two water inlet flows. First of all, we note that the temperature profiles are divided into two areas. The first area starts at the top of the plate to the point where the temperature reaches its maximum. In this part of the plate, the water film receives a sensible heat flux which increases the liquid temperature linearly. In this, it is the heating zone. From the point where the temperature reaches its maximum to the bottom of the plate, we note that the temperature of the plate becomes almost constant and even decreasing. Indeed, in this second zone, the heat flow received by the liquid is fully used in the evaporation process as a latent heat. It is the evaporation zone. Figure 4 shows the effects of wall heat flux on the heat and mass transfer. It is obvious that a higher heat flow density results in a higher temperature along the channel. The evolution of the vapor of time are presented in this figure. After 1 second, the first bubbles of vapors start to be created at liquid film, where the temperature heating was applied. We also noticed that the bubbles began to form from the bottom of the channel. This figure shows the vapor fraction along the plate for different two heat flux. The heat flow is the essential source of energy needed to the liquid-gas change phase. By observing the variation of the vapor fraction, we find that an increase in the heat flux leads to an improved evaporating flow. Indeed, an increase in the heat density generates an energy addition which results in thermal and mass gradient increases. As a conclusion, the results obtained showed that the temperature of the liquid film increases slightly in heating zone, then decreases over most of the plate in the evaporation zone. And the best heat transfer is found when the mass flow rate is lower and when the heat flux density applied is higher. And thank you for your attention.